Today we shall talk about oblique collisions. Oblique collisions are the collisions that are not head-on. So what are head-on collisions? Head-on collisions, as we have understood, are the collisions in which the bodies which are initially moving in a certain direction, after collision they continue to move in the same direction, isn't it? That's how we have seen head-on collisions in the previous videos. So if u1 and u2 are in a certain direction, v1 and v2, though their magnitudes will be different from u1 and u2, their direction will remain the same. So the bodies continue to move along the same straight line in which they were initially moving before collision. So what makes them continue to move in the same straight line? The fact that when the bodies collide, when they undergo a collision over here, let's say like this, the forces, the impact force that the two bodies exert on each other, see, it will be like this. This force, we have discussed this in the previous videos also, that the force of impact that act between bodies during the course of collision, it acts as a normal force, right, which is along the line joining the centers of the two bodies. So it is actually a kind of normal force, and if this force of impact or collision, it acts along the same direction as the initial velocities of the bodies, can we say the only thing that these forces can do is they can change the magnitude of the velocities, right? They can either increase the speed or they can decrease the speed. They cannot change the direction of the speed because the force itself is acting in the direction of the velocity. So the acceleration is in the direction or just opposite to the direction of velocity. So the only thing that it can do is it can change the magnitude of velocity, right? So in fact, just to give some technical terms here, we didn't do that in the previous videos just for the sake of keeping things very simple there. But now that we have understood head-on collisions well, understand that in case of head-on collisions, the line along which the two bodies exert the force of collision or the force of impact on each other, this is called the line of impact. Line of impact is the line along which the force acts between the two bodies. Understand that the direction of force, if it is along the line of impact, can we say that the change in momentum, because we know that the force is directly related to the change of momentum dp by dt or delta p by delta t gives us the force by Newton's second law. Can we say whatever direction the force acts in, the same will be the direction for the change in the momentum suffered by the bodies, right? So it is only along the direction of this impact force that the bodies suffer a change in their momentum. So if the force is acting along the same direction as the velocity directions, the momentum change will happen only in that direction only. So the bodies will continue to move in the same direction, okay? Whereas now if we talk about oblique collisions, what happens in case of an oblique collision then is something different. In case of an oblique collision, the two bodies, when they act, when they come and collide with each other, they collide in such a way so that the direction of impact force, this is the direction of impact force now along the line joining the centers of the two bodies, this is not along the same line as the initial velocities of the bodies. This is the main difference between a head-on collision and an oblique collision. Okay, so the force that the two bodies exert on each other, the force of impact, is in a different direction than the direction of their velocities, and hence the change in momentum suffered by the bodies is in a different direction from the initial direction, and hence due to such a collision then the bodies not just undergo a change in their velocities, they also undergo a change in their direction of motion. So finally it might happen that one body moves like this and the other body moves like this. In some different velocities they will move now after the collision, which will of course depend upon how the force of impact is placed in comparison to the initial direction of velocities. Okay, so it is this type of motion that we are going to study today, and understand that in this case, in case of an oblique collision, the final motion of the bodies is along a plane. It's not just along a single line. So it's kind of a two-dimensional collision, right? When the bodies undergo a collision in two dimensions, they move along a plane, right? But we can simplify such a collision by using the same basics that we have studied in head-on collision, and using them here by making some small variations, some small conditions we have to put, but we can still work with these collisions very easily just by understanding the basics very well. Okay, so let us just understand this slowly and steadily, taking one thing at a time. So once again, if I draw the figure for the two bodies like this, can we say that when the two bodies come just in contact with each other, and this is the line along which they exert forces on each other, let's call this line as the common normal. Common normal, in short we can write it as CN, the common normal. Can we say all the change in the momentum that the two bodies suffer is along the common normal? Why so? Because the force that they exert on each other is along the common normal. The force that they experience on themselves is also along the common normal. So, they will undergo a change in momentum also along the common normal only, right. So, it is only along the common normal that the change in momentum delta P takes place, right, along the common normal. Then the direction which is just perpendicular to the common normal, the one that passes through the point where the two bodies connect with each other, this particular line, we call this particular line as the common tangent. Common tangent, do you see the name is actually according to how the line is, it is actually a tangent to both the bodies, right, both the colliding bodies. In short, we call it as CT, the common tangent. Understand that since the impact forces act along the common normal, which is actually perpendicular to the common tangent, these forces will have no component along the common tangent, and hence the two bodies of masses m1 and m2, let us say, they do not suffer any change in their momentum along the common tangent. So, along the common tangent, whatever momentum they had before collision, they will have the same momentum after collision also, both the bodies individually. M1 will carry its own momentum along the common tangent, M2 will carry its own momentum along the common tangent before as well as after collision. Okay. Understand that the impact forces are still internal, there is still no external force acting on this system of colliding bodies, and hence we can still conserve the total momentum of the bodies, right. So, now that we have understood these basic steps, let us write down a few steps to understand what we are going to do in order to study an oblique collision. The first thing that we have understood is that the conservation of momentum is still valid, right. Why is it still valid? Because the net external force on the system is still 0, right. But we can now go a little deeper now out of the total conservation of momentum, because now the collision will happen in 2 dimensions. We might have to split the whole motion of the bodies along 2 mutually perpendicular directions. So, we will try to split this motion of the colliding bodies along the common normal and the common tangent. It will be easy for us to study the collision while we split the system, the colliding system, along those 2 directions. Why? Because we know that along the common tangent, along CT, the individual momentum of the bodies will remain conserved, remains the same, or it does not change, it remains constant. Why so? We have just discussed this, right. Whereas, now we can say that along the common normal, the total momentum of the bodies, total momentum means the sum of the 2 momentas, right. The total momentum of the bodies remains the same, remains conserved. That comes as a law of conservation of momentum, right. So, law of conservation of momentum is still valid, but we are now applying it over the common normal direction, because we know that along the common tangent, anyway the bodies are not undergoing any change in their momentums, right. Now, the next thing, how do we identify what kind of collision it is? We have discussed the 3 types of collisions in the previous videos. the perfectly elastic collision, the perfectly inelastic collision and partially elastic collision. And we know that one factor that helps us determine the nature of the collision is the coefficient of restitution, right? Coefficient of restitution that we defined in the previous videos. This time in case of oblique collisions, we say that the definition of the coefficient of restitution, definition of E, is also applicable now, but it is applicable only along the common normal this time. Why is it applicable along the common normal? Because all the impact forces act along the common normal. Whatever change in the velocity of separation and velocity of approach happens, that happens along the common normal only. Hence, the definition of E is applicable along the common normal. So, if we are just able to take care of these 3 steps, we can easily solve any question based upon oblique collisions. Okay. There is one exception that can happen in this particular case, that's conservation of momentum is valid because net external force is 0. Sometimes there could be cases where the net external force does not come out to be 0. There we have to be a little careful as to the direction that we choose, where we can still use the conservation of momentum. If we can identify that there is an external force and acting in a certain direction, then we will still be able to conserve the momentum of the system in a direction perpendicular to the direction in which the external force is acting, right? So, those questions would be separate from this one, because here we are saying that the total momentum is conserved. There we have to be careful about the direction along which we use the law of conservation of momentum. But still, if we just take care of the fact that wherever the net force is 0 in whatever direction, we can still use the law of conservation of momentum, we can still solve the questions. Okay. So, as we have understood these 3 steps, let us take a very basic case, a very general case, and see how we use these 3 steps on that system. Okay. So, I will draw this figure once again here. These are the 2 balls, 2 masses, let us say masses M1 and M2, that at any point in time collide with each other. So, they are right in contact with each other right now, and they were initially moving along the horizontal direction. So, U1 as well as U2 both are along the horizontal. Okay. We understand that we can join the centers here to get the direction along which the 2 bodies exert forces on each other, and it is this direction that we call as the common normal, and the direction perpendicular to it we call as the common tangent, right? The masses of the 2 bodies M1 and M2 are given to us, and what else is given to us? We are given the angle that the initial direction of motion of the 2 bodies makes with the direction of the line of impact, the common normal, theta. This angle is also known to us. Understand that here also this angle will be theta. Okay. So, this is important. We need to know the angle that the direction of force of impact makes with the initial direction of motion of the bodies. Now, what we do is, in order to find out the final velocity of the 2 bodies, what we do is we consider the fact that when the 2 bodies just after collision start moving, they have some components of velocities. Along which directions do we take the components now? I will tell you here. So, we know that this is our direction of common normal, right, and this is our direction of common tangent. We already know that along the common tangent there is no change in the momentums of the bodies, it is only along the common normal that the momentums change. So, what we do now is, for the sake of convenience, so that we can use our equations carefully, what we do is the final velocities we take as components along the common normal and along the common tangent. The final velocities of the 2 bodies we take as the components of the velocities along the common normal and common tangent. Just see how we do this. So, let us assume that the first body, the one that has a mass m1, finally soon after the collision, it moves along the common normal with the velocity v1, and along the common tangent it moves with the velocity v2. So, understand that v1 and v2 are only the velocity components. We can always find out the net velocity of the mass m1. Velocity of mass m1 will be nothing but square root of v1 squared plus v2 squared, and we can find out its direction also, right. Similarly, let us assume that the second body of mass m2 moves along the common normal soon after collision with a velocity v3, velocity component v3, and along the common tangent it moves with a velocity component v4. So here in this case we have to find out 4 variables, v1, v2, v3 and v4. All the 4 are variables for us and we have to find out their values, for which we would require 4 equations, isn't it? So which 4 equations do we use here? The same equations that we get from the above 3 steps. So we'll use those steps one by one now and we shall write equations according to that, and you shall see how we get all the answers. So the first step here, step 1 is that the individual momentum of the bodies, individual momentum is conserved along the common tangent, right? Along the common tangent they do not exert any force on each other, so their momentums will not change along the common tangent. Now look at the figure carefully and identify what is the initial momentum of the mass m1 along the common tangent. This is the initial velocity u1 and u1 makes an angle theta with the common normal. So understand that the component of u1 in the common tangent direction will be u1 sin theta, right? This component. So what will be the momentum along that direction? It will be m1 u1 sin theta, right? This is the initial momentum of the mass m1 along the common tangent. And what should this be equal to? This should be equal to the final momentum of the mass m1 along the common tangent, which if you look at this figure here will be nothing but m1 v2, right? So m1 v2, right? See that from this equation, knowing the value of u1 as well as theta, as m1 cancels out, we can directly get the value of v2. v2 will be nothing but u1 sin theta. So from this one equation itself we have obtained the first component v2, the final velocity of the mass m1 along the common tangent we have obtained. When we use a similar equation for the mass m2, can we say the initial momentum of m2 along the common tangent along this direction, this velocity component will be u2 sin theta on the same lines, right? So that m2 u2 sin theta, we can write it to be equal to m2 into what is the final velocity component along the common tangent, not v3, v4, right? v4 is the final component. So m2 v4, this is the final momentum along the common tangent for the mass m2, and as you can see this will directly give us the value of v4 as u2 sin theta. Second equation, right? From 2 equations we have already got the 2 components v2 and v4 already. Now we use the second step. What is the second step? The second step is that the total momentum of this system of 2 bodies is conserved along the common normal. Step 2, total momentum is conserved along the common normal. Along the common normal, the sum of the 2 momentas will be equal before and after collision. So what is the momentum of the 2 bodies before collision along the common normal? See, once again u1 is in the horizontal direction, its component along the common normal will be u1 cos theta. Similarly, the component of u2 along the common normal will also be u2 cos theta. So can we say the total momentum before collision will be m1 u1 cos theta plus m2 u2 cos theta, and this should be equal to the final momentum along the common normal. v1 and v3 are the 2 velocity components along the common normal for the both the bodies. So m1 v1 plus m2 v3. This equation we can call as equation number 3. This is an equation in v1 and v3, these 2 variables, connecting these 2 variables, right? So this is the third equation. And the fourth equation now comes from the definition of E, the coefficient of restitution, which basically tells us the type of collision this is, right? So for step 3, we say that the definition of E is only along the common normal. We use it along the common normal. What is that? If you remember from the last video, the definition of E is, it is the velocity of separation divided by the velocity of approach. That's how we studied the definition of E in the previous videos, right? Now we are saying that we have to just extend this definition to the common normal direction. We can use the definition of E only along the common normal. So, we will write velocity of separation along the common normal by the velocity of approach along the common normal. So, we will have to make this slight modification here. Now, look at the figure once again carefully. Velocity of separation after collision along the common normal. Along the common normal, the mass m2 is moving with v3 and the mass m1 is moving with v1 along the common normal. Can we say the velocity of separation, the velocity with which m2 separates away from m1 will then be v3 minus v1? That is nothing but the relative velocity with which m2 is moving with respect to m1, right. So, in the numerator we will have v3 minus v1 as the velocity of separation after collision, right. What about the velocity of approach before collision? Before collision along the common normal, m1 is moving with u1 cos theta and m2 is moving with u2 cos theta. So, can we say the approach velocity with which m1 is approaching m2 will be u1 cos theta minus u2 cos theta? So, that becomes the velocity of approach, u1 cos theta minus u2 cos theta, and this is nothing but E, and this becomes our fourth equation then. So, 4 variables, 4 equations, we can solve for all the 4. It is quite interesting to see that the first 2 variables we have obtained from the first 2 equations itself, and the equation 3 and 4 you can combine together now to get the values of V1 and V3. So, if you remember these basic things, basic rules, you can deal with any type of oblique collision, though there are some special cases here that we study. Just as we studied the special cases in a perfectly elastic collision, head-on collision, right, in the previous videos, we say that on the same lines, if we have perfectly elastic oblique collisions, perfectly elastic oblique collisions, what happens here? Do you all remember that for case of a perfectly elastic collision, oblique collision, in this case what happens is E takes a value of 1. So, one thing is this above equation that you have written here, this will become V3 minus V1 is equal to u1 cos theta minus u2 cos theta, which you can combine easily with the third equation written above to get your answer, right. That is one thing, because we know that perfectly elastic collision has E is equal to 1. Apart from that, do you all remember we have discussed some special cases in case of a perfectly elastic collision? Yes. So, we say that in this case also we can use all the results that we derived in a perfectly elastic head-on collision, all the results of perfectly elastic head-on collisions are valid, but just with one condition. What is that condition? They are valid along the common normal. Why? Once again, because of the fact that all the impact forces act along the common normal. So, all the changes that take place in the two bodies in their momentas, they happen along the common normal. So, the definition of E is applicable along the common normal, and all the special results that we have obtained, they are also applicable along the common normal. Now, what were the special results? If we just talk about a couple of cases, the first special case that we discussed in a perfectly elastic collision was when two identical bodies collide with each other, m1 is equal to m2, right. In case of two identical bodies colliding each other, we said that the result that we get is that the velocities of the two bodies get interchanged, right, upon collision. So, now what change do we need to make in this results? We will get that, we will say that the velocities will still get interchanged in case of an oblique collision also, but where? Only along the common normal. Okay. So, how do we see this? Let us take a small example for this. Let us say there is a body of mass m which comes and hits another body also of mass m, though I have shown two different sizes, just for the sake of being able to identify the two bodies, understand that their masses can still be the same, right? So that when they collide with each other perfectly elastically, if that is the case, and it is an oblique collision, it is not a head-on collision now. So, and what way were they moving initially? Let us assume that the first body was moving with a velocity of v naught and the second body is, let us say, at rest. It is not moving. So that when this second body comes from behind and hits the first body, they exert forces on each other along the common normal, and it is only along the common normal that they interchange their velocities. So, if we assume that the direction of common normal makes an angle theta with the direction of initial direction of motion of the first body, can we say that the component of its velocity along the common normal here will be v naught cos theta, and the component of v naught along the common tangent will be v naught sin theta, right? So, along the common normal, the component of velocity that is there, it will get interchanged. What does that mean? That the first body will lose all of its velocity v naught cos theta, and the second body will gain this velocity v naught cos theta along the common normal. So, what will happen after the collision? After the collision, the smaller body, still having a mass m only, will have lost all of its momentum along the common normal, because it has taken the momentum of this body which was at rest. So, 0 velocity along the common normal for the first body now after collision. It moves only along the common tangent with whatever velocity it had earlier, because along the common tangent we know velocities are not going to change. So, the first body moves with v naught sin theta along the common tangent, and what will happen to the second body? The second body has now gained the velocity of the first body along the common normal, which is v naught cos theta. So, the second body of the same mass will move with v naught cos theta along the common normal. Understand that this is the common normal direction and this is the common tangent direction. So, in this case we can say that the two bodies move perpendicular to each other after collision, isn't it? So, this angle will be 90 degrees here. In fact, there are questions that are directly based upon this particular aspect. If you understand that a body coming from behind, if it hits an identical body placed at rest, after collision the two bodies will move perpendicular to each other, because one will move only along the common tangent and the other will move only along the common normal, right? So, this is one of the special cases that we studied in perfectly elastic head-on collisions, and now we are using those results directly in an oblique collision also. The second case, let us take that also. The second special case that we discussed was case 2, where a very light body comes from behind and hits a very heavy body placed at rest. Do you remember what happens there? We remember taking the case of a ball which goes and hits a wall, right, a very heavy wall. And if this ball is moving with a velocity v naught and it hits the wall with v naught, we know that after collision this ball will rebound with the same velocity v naught in case it is a perfectly elastic collision, right? So, if we have to use this result in case of an oblique collision, how do we use it? We use it like this. So, if we just take the ground, the ball coming and hitting the ground, let us say, the understanding of that becomes a little easy. If a ball comes and hits a ground with velocity v naught, we know that it will rebound with the same velocity v naught. This is for a head-on collision, right? What happens in case of oblique collision? Similar oblique collision would be like this. If this is the ground and a ball comes and hits the ground at an angle now, let us say it hits the ground making the velocity of the body making an angle theta with the vertical direction. Now, when this ball comes and hits the ground, do you understand that this will be the direction of common normal, the one that joins, the one which is perpendicular to the two bodies, the ball as well as the ground. So, this is the common normal, whereas along the ground this direction will be the common tangent, right. So, according to the special result that we have for this case, the body gets rebound only along the common normal now. So, what is if we assume that the ball is coming with a velocity v naught, making an angle theta with the vertical, that is along with the common normal. Can we say that the component of this v naught along the common normal, because this angle will also be theta, this component will be v naught cos theta, and we are saying that it is this component of velocity which will now rebound, which will just become minus of v naught cos theta. It will just change its direction and will move with the same magnitude. Whereas the component along the common tangent, which in this case will be v naught sin theta, will not change. So what will happen soon after the collision? Soon after the collision, the ball will be somewhere here with its common tangent component of velocity remaining unchanged. So v naught sin theta remains v naught sin theta, whereas v naught cos theta, which was downward now, will become upward, v naught cos theta. Do you understand? So the ball will move along this direction now. Understand that it will make the same angle theta with the vertical as it was making earlier, because it is a perfectly elastic collision. The velocity with which it rebounds upward is the same as the velocity with which it hits the ground, right? So in that way we can easily find out the final velocity of this hitting ball. Now let us come back to the general cases now. This is the case where the collision is perfectly elastic. What if the collision is not a perfectly elastic collision? What if it is a partially elastic collision with a coefficient of restitution E over here at the ground? This we can take up as an example itself. So let's say there is a case where we have a ball which comes and hits a ground in a direction which makes an angle theta with the vertical or the direction of common normal, and the coefficient of restitution here is E, the coefficient of restitution associated with the collision that happens between the ball and the ground is E. We are supposed to find out the final velocity of the ball and its final direction of motion. So if we assume that, let's say the incoming ball has a velocity v, it hits the ground with a velocity v naught, and finally if it goes out with a velocity v, making a final angle phi with the vertical direction, we are supposed to find out both v as well as phi. What all do we know? We know v naught and theta and E also, the coefficient of restitution also we know. Okay. So let us try to use the same basics that we have studied before. The first thing, identify the directions of common normal and common tangent. What is the common normal? When the ball comes and hits the ground over here, if you try to join the center of the ball with the ground, normal to the surface along which the two bodies collide, can we say this vertical direction will come out to be the common normal direction, right? What will be the common tangent then? The direction perpendicular to this common normal direction will be the common tangent direction, right? So this is the common tangent. And now we come to our results. What are the results? We know that along the common tangent, the ball does not suffer any change in its momentum. So if we look at the figure, this angle here will be theta. So the component of v naught along the common tangent will be v naught sin theta, whereas along the common normal it will be v naught cos theta in the downward direction, right? Whereas if we assume that the final velocity of the ball is v and the angle that it makes with the vertical is phi, we can say that its component of velocity along the common tangent after collision will be, because this angle will also be phi here, it will be v sin phi, and the component of velocity along the common normal will be v cos phi, right? Now let us write the results. What's the result? The first result is along the common tangent, no change in momentum. So along the common tangent, can we say the initial momentum, which is m v naught sin theta, is equal to m v sin phi? Do we see that this is the final momentum along the common tangent, right? So this is the first equation that we get. We see that m gets cancelled, so we get a relation between v and phi in terms of v naught and theta. Along the common tangent, along the common normal now, can we use the definition of E? Can we say that E is equal to the velocity of separation along the common normal after the collision? After the collision, the ball goes away from the ground along the common normal with a velocity of v naught cos phi. So can we say v cos phi. So can we say v cos phi then will be the velocity of separation of the ball from the ground after collision along the common normal? divided by the velocity of approach before collision along the common normal. Before collision, the ball is moving towards the ground with a velocity of v naught cos theta along the common normal, right. So, can we say the ball is approaching the ground with a velocity v naught cos theta along the common normal, v naught cos theta. So, this becomes our second equation. Do we see that we can from this equation now we can write E times v naught cos theta is equal to v cos phi. Let us call this as equation number 2 instead of calling this one. So, now we can solve 1 and 2 together by dividing the two equations. Do you see that when we do 1 divided by 2, we shall get v naught will cancel out on the left hand side and we will have tan theta by E is equal to, on the right hand side v cancels out and we have tan phi, right. So, here what we are getting is a relationship between the angle phi and angle theta in terms of E. So, if we know the value of E and we know the value of theta, we can easily find out the angle phi. How can we find out the value of V then? We can square and add the two equations. Can we say we can do first equation squared plus second equation squared will give us, on the right hand side terms I am writing first, it will be v squared sin squared phi plus v squared cos squared phi, which we know we can take v squared common where and this term will become 1, is equal to, on the right hand side we have v naught squared sin squared theta plus E squared into v naught squared cos squared theta, right. So, this can again be solved. We can say that v squared from here will become nothing but, you can take v naught square out and inside you will have sin squared theta plus E squared times cos squared theta. So, if you want you can find out the speed, final speed of the body as well. So, using the same basics then we can solve any such type of problem. In the next video we shall take up some standard problems that are based upon the oblique collisions and we will see how we use the same basic concepts there also.